let's look at several more examples of coming up with trigonometric substitutions. So in these examples, we might not work them all out to the very end, but at least we'll do the trigonometric substitution part. So on this first one, the part that draws my eye, the part that suggests a trigonometric substitution, is this square root part. And it's a difference of squares where the variable part is negative, and that's the situation where we'll use sine. Okay, so, and because there's a 1 right here, we'll have a 1 right there. So then dx is cosine theta d theta. And now we can do the substitution. So in the numerator, x squared, that's sine squared theta. In the denominator, so 1 minus sine squared is cosine squared, and the square root of that is cosine. And then dx is cosine theta d theta. So the cosines cancel, and we're integrating sine squared theta. If we want to, we can translate the bounds at the same time. These bounds are sort of nice to translate into theta values. So if x is 0, what angle makes sine of the angle 0? That would be 0. And if x is 1, what angle makes sine produce 1? Well, it's pi over 2. Okay. Now we can, let's see, for this integrand, now we have to use all our trig integrating tricks. And for this particular one, just use a double angle identity. So integral from 0 to pi over 2 of 1/2 1 minus cosine 2 theta. And I think this is a good place to stop. At this point, it's a relatively routine integration problem. You might need to do a little u substitution to handle the 2 in there, but on the other hand, you might just be able to write down the antiderivative without doing a u substitution. All right, so general lesson here is when you have a difference of squares and the constant part is positive and the variable part is negative, that's when we're going to use sine. One other situation where this can be useful is in something like this, where we have 1 minus x squared to the 3/2. So don't get too dependent on that square root actually being written down. The square root might be hiding, or it might not be there at all. Right here, it's sort of hiding because this exponent with a 1/2 in it is kind of like having a square root. So this suggests that we might want to use a trigonometric substitution in this situation, even though it's not staring us in the face like it would be if we had this sort of square root in the problem. So we'll do a square root. Because it's a difference of squares with the variable part negative, we'll use the sine version of trigonometric substitution. So we'll let x be sine theta, and dx will be cosine theta d theta. So now we can do our substitution. So integral of dx is cosine theta d theta. In the denominator, we have 1 minus x squared, so 1 minus sine squared, that's cosine squared, theta to the 3/2. But now the squaring and the power of a half, those cancel, right? We're multiplying the power of 2 and the power of 3 over 2. That gives us a power of 3. So we get integral of cosine theta d theta over cosine cubed theta. And then we can cancel a cosine here, and we get the integral of 1 over cosine squared theta d theta. And I think I'll leave it there. This, if you sort of are a little creative with your trig functions, you should be able to rearrange this into a trig integral that you know. Okay, let's look at another example. So if we have a difference of squares where the constant is positive and the variable is negative, we'll use the sine version of trig substitution. If we have a difference of squares where the variable part is positive and the constant part is negative, that's when we're going to use secant. Oh, I've left off an a here. If it's minus a squared, then we have an a in our substitution here. So 1 over, if we're going to integrate 1 over square root of x squared minus 9, so 9 is playing the role of a squared, so a is really 3 here. That means we should let x be 3 secant theta. That means dx is 3 secant theta d theta. No, 3 secant theta tangent theta d theta. So our integral turns into, see, this denominator is square root of 9 secant squared theta minus 9. And the numerator is just dx, which is 3 secant theta tangent theta d theta. Okay. So you might just remember what this denominator simplifies to, but if you don't, you can factor out that 9 and then move it outside of the square root, where it becomes 3. And the stuff inside the square root is now secant squared theta minus 1. On top we have 3 secant theta tangent theta d theta. These 3's cancel. And then hopefully you remember secant squared theta minus 1. There's a trig identity for that, right? The Pythagorean identity for secants and tangents says that this is just tangent squared theta. And then we take a square root. So the square root and the square cancel here. So we get integral of secant theta tangent theta d theta all over tangent theta. Now our tangents cancel, and we're left with a trigonometric integral that you should know or be able to look up. All right. If instead of a difference of squares, we have a sum of squares, that's when we're going to use our tangent substitution, and I've left out my a again. There should be an a in there. So for this particular integral, it looks like the role of a is being played by the number 4. So x is going to be 4 tangent theta, right, since 4 squared is 16. So dx is 4 times secant squared theta d theta. And now we can rewrite our integral. Integral of, so x squared is, right, looking here, x squared is 16 tangent squared theta over square root of 16 plus x squared, which is 16 tangent squared theta, times dx, which is 4 secant squared theta d theta. All right, now we can start simplifying things. This stuff in the denominator, right, you can factor out the 16 and move it outside the square root. The stuff left over is 1 plus tangent squared theta. 1 plus tangent squared theta is secant squared theta, and the square root of that is just secant. So this denominator is 4 times secant theta. Numerator is 16 tangent squared theta, and then over here we have 4 secant squared theta d theta. Now we can start simplifying, get rid of a factor of 4, get rid of a factor of secant. We're left with, let's see, integral of 16 tangent squared theta times secant theta d theta. All right, now this integral is actually a bit tricky. So the way to handle this integral, I won't do it, but the way to handle this integral is to use integration by parts and then use a trig identity to make this integral reappear and then solve the resulting equation for this integral. But I'll stop here with this example. All right, next example. So let's see. This one is, let's see, the square root part sort of draws the eye. Inside the square root we have a difference of squares, not a sum of squares. A difference of squares, so we're going to use either sine or secant. But the variable part is positive here. And when the variable part is positive, that's when you use secant. So we'll use x equals, right, now we need the square root of this number, so square root of 1 is 1. So x equals secant 1 times secant theta. Dx is secant theta times tangent theta d theta. Now we can rewrite our integral. So this, in the numerator, we get secant squared theta plus 1, sorry, minus 1 over x, which is secant theta, times dx, which is secant theta tangent theta, d theta. Cancel a factor of secant. So integral of, so square root of secant squared minus 1, that's square root of tangent squared theta times another tangent d theta. And the square root of tangent squared is tangent. And then we have another tangent, so now it's squared again. Okay. And then we're left with this integral. If you don't know how to handle this integral, then try using a Pythagorean identity for tangent and secant again. Tangent squared is secant squared theta minus 1. And then you can integrate secant squared because that's a known trigonometric derivative. All right, let's move on. How about this one? 1 over x squared plus 4. So again, the x squared plus 4 part catches the eye. That's a sum of squares. And if you have an inconvenient sum of squares, then often tangent, using a trigonometric substitution with tangent, is the way to go. But since it's plus 4 here, we need the square root of 4 in front of our tangent, and that's 2. And then dx is 2 secant squared theta d theta. And now we can do our substitution. So let's see, integral of 1 over square root x squared, so 4 tangent squared theta plus 4, times dx, which is 2 secant squared theta d theta. All right, now we need to simplify the stuff in the denominator there. I'll let you work through the algebra and trigonometric identity, but when you do simplify all of this, you get 2 secant theta, I think. Let's see, factor out the 4, that's a 2. This turns into secant, yeah. Okay, times 2 secant squared theta d theta. But then the 2's cancel, a factor of secant cancels, and we get the integral of secant theta. And the integral of secant is a known integral. That's natural log, absolute value, secant theta plus tangent theta plus a constant. And then we aren't quite done. Remember, we need to undo our substitution to get back to the original variable. Just to do that one more time, let's see how that works. The general idea is to use the substitution equation that we first used at the very beginning to draw a right triangle that sort of is a picture of this equation. To do that, it's nice to have the trig function by itself. So let's isolate tangent theta. We get tangent theta is x over 2. So we need to draw a right triangle that has theta for an angle, and so that tangent of theta is x over 2. So here's a right triangle. If we put theta down here, tangent theta is opposite over adjacent, so we need x over here, 2 on the bottom, and that means the hypotenuse is the square root of x squared plus 2 squared, which is 4. And then we can use this picture to write any trig function we want. So natural log, absolute value. Secant is hypotenuse over adjacent, so square root x squared plus 4 over 2, plus tangent theta, which is opposite over adjacent, so x over 2, plus a constant. And there we go.